Welcome students. I am Dr. Smita Sharma, Associate Professor in Physics, Government Dungar College, Bikaner. In this slide, we will discuss the AC analysis of the differential amplifier. In the previous lecture, the topics that were covered were circuit configuration of a differential amplifier, dual input balanced output differential amplifier was discussed in detail, and the DC analysis of the amplifier was carried out. Now in this lecture we will discuss the AC analysis of dual input balanced output differential amplifier. First we again see the circuit diagram of dual input balanced output differential amplifier. So in this circuit there are two input signals VIN1 and VIN2 that are applied to the bases B1 and B2 of the transistors Q1 and Q2, and output voltage is measured between the two collectors C1 and C2, which are at the same DC potential. Now we wish to carry out the AC analysis of this circuit. Now why AC analysis is carried out? AC analysis helps us to derive an expression for the voltage gain, because this is an amplifier, so we are interested in its gain of voltage gain. So by doing AC analysis we derive an expression for voltage gain, and input resistance can also be calculated, that is of the differential amplifier. Now what we will have to do in order to carry out AC analysis? In order to perform an AC analysis, we need an AC equivalent circuit. In the same way, before when we had carried out DC analysis, we had made a DC equivalent circuit. Now here we will design AC equivalent circuit. Now how can AC equivalent circuit be made? This can be made by following 2 points. First, plus VCC and minus VE, that is the two batteries are set to 0. Second, the transistors are replaced by their T equivalent model, small signal T equivalent models. Now following these 2 points, the AC circuit is as shown. So we will carry out AC analysis of dual input balanced output differential amplifier. So this is AC equivalent circuit of the dual input balanced output differential amplifier. On looking through the diagram, on the left hand side is the equivalent circuit of the first section of the differential amplifier, and on the right hand side it is the second section of the differential amplifier. These are represented by by written as Q2. The related terms are all represented by symbol 2, and the Q1 transistors terms are all related by symbol 1. E1 and E2, both the emitters are connected as shown in the center. B1 B2 are shown on in first loop and second loop, and C1 and C2 are shown at the far end, left hand side and right hand side. Input has been provided at the base B1 and base B2 of the two transistors. These are the input and output waveforms, the way they are given and they are provided. Now first of all, by the AC analysis we were saying that we can calculate the voltage gain. So we'll calculate the voltage gain. For this we'll have to consider following points. IE1 is considered equal to IE2, so that the two AC emitter resistances of transistors Q1 and Q2 are same, and thus they are denoted as shown in figure by RE. Also, the voltage across each collector resistor is shown out of phase by 180 degree with respect to input voltages VIN1 and VIN2 as shown in figure. The VIN2 polarity is just opposite to that of collector voltage in both the side, on both the sides, left hand side and right hand side. This is because the configuration that we have chosen is common emitter configuration, in which if the input voltage is positive, then the output is always negative going. If input is positive going, then output is negative going. Now this is again the same circuit. Now we'll carry out the mathematical analysis. One more thing that we have considered here is, as seen from the diagram, V naught is the voltage between C2 and C1. Here we have written a positive sign near C2 and negative sign near C1. This is because the sign polarity of the output voltage V naught indicates that the voltage at collector C2 is assumed to be more positive with respect to that at collector C1, even though both of them are negative with respect to ground. So by diagram we can see the ground terminal is noted as plus and C1 is noted as minus. In the same way, the ground terminal at C2 is given plus and C2 is negative. This means ground is more positive with respect to C2 or C1. But on comparing C2 and C1, we have assumed that C2 is more positive with respect to C1. So the signs are shown in the as shown in the diagram. Now two loops are clearly shown in the figure 1 and 2. We will write Kirchhoff's voltage equation for the two loops. These are simple equation 1 and 2. These can clearly be understood. VIN1 has positive sign and the current flow indicates all the equation 1 and 2. Now here in place of IB1 and IB2 we can use the relations IE1 upon beta AC. This is because current gain is defined as beta, which is always equal to IB upon IE1, IE upon IB. So we can replace IB1 by IE1 and beta AC. On replacement, we finally obtain the two relations. Now this can further be simplified if we consider IN1 upon beta AC to be very small. Generally it is very small, so we neglect them, and finally the leftover terms can be rearranged in terms of IE1 and IE2. We get equation 3 and 4. So the simplified version of equations 1 and 2 are 3 and 4. Here IE1 terms are kept at one place and IE2 terms are kept at one place. So this creates two simultaneous equations, and these can be solved so that we can obtain IE1 and IE2. So it can be solved by either method. Here I have used Cramer's rule to solve it, and any method can be used. So we finally obtained IE1 and IE2 in equation 5 and 6. This you can solve in your copies, and it is very easy to obtain. Now we have calculated IE1 and IE2. Now we will calculate the output voltage. Now see in the diagram, uh, we have to calculate output voltage. Now we have considered C2 to be more positive with respect to C1, so output voltage will simply be Vc2 minus Vc1. Now what will be Vc2? Now Vc2 is the voltage at the collector C2, and there is resistor RC between Vc2 and collector and ground, and we know voltage of ground is always 0. So and ground is more positive with respect to collector, so what we can write, uh, 0 minus Vc2, that is the potential difference, because 0 is greater, more positive, so we will write 0 minus Vc2 is equal to the current and the resistor, product of current and resistor in between. So what is the current and resistor? Resistor is RC and the current is IC2. So what we can write, 0 minus Vc2 is equals to IC2 into RC, or taking the minus sign on the other side, what we get, Vc2 is equal to Ic2 into Rc, that I have written here. In the same manner we can calculate Vc1. On further simplification, we obtain Rc into Ic1 minus Ic2. Now generally we consider IE and IC currents to be approximately same. So we can replace IC1 and IC2 by IE1 and IE2. So output voltage will be RC IE1 minus IE2. Now putting the values of IE1 and IE2 as they were calculated before, and finally solving, we obtain the output voltage as shown by equation 8th. Now in equation 8th, it is clear that a differential amplifier amplifies the difference between the two input signals as it was expected. But now we want to calculate the voltage gain. The voltage gain, in order to calculate the voltage gain, we need two things: one, output voltage that we have calculated, and the input voltage. Here in this case, because there are two ends and two inputs are provided, so we need difference in input voltages. So VID is defined as VIN1 minus VIN2, that is the difference in the input voltages. So the voltage gain of dual input balanced output differential amplifier AD will now be output voltage upon input voltage equal to VO upon VID. On simplification, we finally obtain it is equal to RC upon small re. So this is the voltage gain of the dual input balanced output differential amplifier. Now we can, other parameters that can be calculated are differential input resistor, output resistance, and current gain. But before discussing them, we will first consider the inverting and non-inverting inputs. So now inverting and non-inverting inputs. In the differential amplifier circuit, the input voltage VIN1 is called non-inverting input because a positive voltage VIN1 acting alone produces a positive output voltage. This can be seen from the formula below. We note if we keep VIN2 equal to 0, then the output voltage is always positive, as VIN1 is positive. So this end is always termed non-inverting input. In the same way, the positive voltage VIN2 acting alone produces a negative output voltage. If we keep VIN1 to be 0, then output voltage will be minus of Vin2. So this Vin2 is called inverting input. Consequently, the base terminal V1 to which input Vin1 is applied is referred to as non-inverting input terminal, and the base terminal V2 to which input Vin2 is applied is referred to as inverting input terminal. But these two terminals can always be interchanged. Here we have considered two terminal to be the collector C2 to be more positive with respect to uh, C1. So these two inputs can always be interchanged. Now we'll calculate differential input resistance using the same AC equivalent circuit. Now first of all, we'll define what do we mean by the input resistance. It is defined as the equivalent resistance that would be measured at either input terminal with the other terminal grounded. So what is the definition? First of all, make one of the input terminal ground, so there will be no signal and it is directly connected to the ground, and we are measuring the input resistance at one of the terminals. That resistance is termed as differential input resistance. This means that the input resistance Ri1 seen from input signal source Vin1 is determined with the signal source Vin2 set at 0 and vice versa. So if we calculate Ri1, then we'll have to put Vin2 to 0, and if we want to calculate Ri2, then we will have to put Vin1 to 0. Generally, RIN1 and RIN2 are very small, so in this derivation they are ignored. Now, mathematically RI1 can be defined as VIN1 upon IB1, voltage upon current, input signal voltage, and the current flowing through it, base current is flowing through it, so base current. And what is the condition? Vin2 should be 0. Now again, in place of IB1 we have replaced them with the help of with current gain and emitter current as shown in the equation. Now we know the value of IE1, so we are putting it and simplifying it, so we get Ri1. Now in this equation of Ri1, what we have to do, we have to calculate what we have to put the condition Vin2 equal to 0. When we place it and further simplify it, we get the following equation. Now this equation can further be simplified by considering Re is very much greater than small re. So generally Re is neglected as compared to Re. So in place of Re plus 2 capital Re, we can write 2 capital Re, and in place of small re plus capital Re, we can write capital Re. So further approximating, we finally obtain Ri1 equal to 2 beta AC into Re. So this is the input resistance at the terminal first, when the signal source at the terminal 2 is kept at 0. In the same way, we can calculate Ri2, and it also comes out to be 2 beta AC Re. Now we'll calculate the third parameter, that is output resistance. This its calculation is very simple, but first we'll define what do we mean by the output resistance. It is defined as the equivalent resistance that would be measured at either output terminal with respect to ground. किसी भी आउटपुट टर्मिनल पर, at any output terminal with respect to ground, we can calculate the resistance, and that resistance will be the output resistance. So the output resistance RO1, what will be RO1? It will be measured between C1 and ground. This already we have calculated. What was it? It was equal to collector resistor RC. Initially we had calculated it. So RC1 is equals to RC2 is equals to RC. This is the output resistance. Now fourth parameter that we calculate in AC analysis is the current gain. The current gain of the differential amplifier is undefined, so we do not work it out. This is because differential amplifier is a small signal amplifier, so it is generally used as a voltage amplifier and not as a current or power amplifier. So we generally do not need to calculate current gain. So here, by doing AC analysis, we have calculated the four parameters essential to study a differential amplifier and to study its signal response. Now in coming slides we'll see what else is needed to make an operational amplifier, because we have studied differential amplifier. Now one more important property has been missed, that is common mode rejection ratio. In the next slide we'll first cover the common mode rejection ratio, and then we'll take the other two things, that is level translator and constant current source, to make these two are also essential to make an operational amplifier. Thank you.